Lasers are devices that produce nearly parallel and monochromatic coherent beams of light. They're commonly one color or one tone of color. They produce this effect by exciting atoms to higher energy levels and causing them to radiate their energy in different phases. Lasers have the potential to cause serious eye and skin injuries if they're not used properly. Here at Ryerson University, lasers are predominantly utilized in some engineering and physics laboratories. Always be aware of the class of laser that you're working with. Laser classes range from Class 1 through Class 4, where Class 1 is the least hazardous and Class 4 is the most. Class 1. This class of laser is safe under all circumstances. Class 1M. This class of laser is considered safe as long as optical instruments are not used. Optical instruments include telescopes, binoculars, magnifying glasses, but not prescription glasses. Class 2. This is the first class of visible lasers. They are considered safe and allow for accidental exposure of less than a quarter second. Class 2M. Class 2M lasers are considered safe and allow for accidental exposure of less than a quarter second, as long as you're not using any optical instruments. Class 3R. Class 3R lasers are not considered safe, however, are considered to be a low safety risk. Class 3B. This class of lasers is considered hazardous. The radiation from these lasers can damage the eyes and skin. Viewing from a diffuse surface is considered safe. Class 4. This is the highest class of laser. Direct viewing and viewing from a diffuse surface can cause damage to the eye. These lasers are capable of starting fires and present an extreme hazard to the skin. When working with laser machines, it's important that the alignment process be well performed to avoid eye and skin injuries. Take note of the following during a laser alignment. Before starting the alignment, identify equipment and materials that are necessary to perform the alignment safely. Ensure that you have protective eyewear with the appropriate value of optical density for the beam power. Using high optical density eyewear that is suitable for normal operations with low power alignment beams is a formula for failure, as is wearing low optical density alignment eyewear for high power beams if low power or simulated beam low power lasers are used. Make sure you change to goggles with correct optical density when aligning the last optical components at full power. Check all personal protective equipment, such as blocks that will stop laser light. Also determine if the power of the laser has the ability to start a fire. Pay attention to housekeeping. Make sure the immediate work area and bench, as well as the top optical table, is free from opportunistic specular or mirror-like reflectors that are not needed for the alignment. This can include glass bottles, razor blades, forceps, screwdrivers, optical post, photographic paper, plastic, or dye cells. Remove all shiny objects from hands, wrists, ankles, ears, and neck that may be reflectors and are electrically conductive. If jewelry is not easily removed, such as a wedding band, Cover it with multiple layers of electrical tape. Tools, targets, beam stops, and blocks, power meters and detectors, beam profiling systems should be carefully placed in appropriate spots on the optical table. Always have as few materials present as possible. Ensure the proper use of curtains, signage, caution tape to protect your work area, as well as any nearby persons. Make sure tools or items used in and around the beam path have non-reflective properties. Check diffusing surfaces at the wavelength to be aligned. View beams indirectly by using remote viewing, thermal paper, ceramic discs, or infrared or ultraviolet viewing. You may also use viewing scopes, paper business or 3x5-inch cards, and phosphor viewing cards. Remove materials in shirt pockets that could fall into the beam path. Prepare the beam delivery system. Remove beam tubes or other parts of the protective housing as necessary, including extended sections that may be covered by beam tubes or bellows. Check all optics, such as mirrors, lenses, filters, polarizers, and expanders, and optomechanical components, such as base plates, post holders, fasteners, and mirror mounts, ensuring that they're securely mounted and correctly aligned. Make sure that the beam shutter is closed or a beam block is in front of the end window. Make sure the beam block is securely mounted. Use the minimum beam power or energy for as many alignment steps as possible, or use a low-power coaxial laser beam for path simulation. In some cases, power-reducing filters, such as neutral density filters, may be used during alignment. For continuous wave lasers with adjustable power, adjust the power to a minimum stable level. For pulsed lasers, use single pulses and/or reduce pump power. For Q-switch lasers, turn off the Q-switch and operate in low-power, continuous wave mode. Replace the laser with a low-power coaxial laser, reduced below the maximum permissible exposure limit, for aligning all optical components when possible. Align the optical component starting with the component nearest the laser, and continue one component at a time away from the laser. Always use beam stoppers during this process. During this process, be aware of the potential for stray beams from components such as polarizers and dielectric mirrors. Check for stray beams at each step. Be careful, as many surfaces that appear dull can actually act as mirrors. Class 4 lasers should be terminated with flammable retardant materials. Check these materials periodically for damage. Special controls for ultraviolet lasers. Protect your skin in addition to your eyes. Make sure your hands and face are covered. Ensure control for ozone production. Special controls for picosecond and femtosecond lasers. Eyewear should be M-rated, which has been tested for very short pulses.